Hello, my name is Robert Bennett. I'm a principal engineer at Magee Technologies, also known as MTEC. Today I will show how application of MTEC's technology will increase submarine development efficiency through a more robust structural simulation planning and approval process. The savings impact is estimated to be several $1,000,000 per occurrence and will avoid delays to the structural approval process, which can be 8 to 10 months each. In addition, this technology will add confidence in the structural analysis solutions, which will lead to optimized submarine performance while maintaining safety. All structures of any complexity are being designed through structural simulation using finite element model analysis, often referred to as FEM analysis or just FEM. I'm going to explain that disagreements in chosen FEM analysis approach cause significant schedule delays. MTEC's robust, validated FEM analysis guidelines offer an efficient development process which can be extended to structural optimization. For prime contractors that may be wary of added requirements, so far the developed guidelines are not requiring significant changes to existing analyses. If anything, establishing approved processes at an early stage of development should avoid expensive analysis rework and maintain budgets and schedules. As you listen to this presentation, we ask that you think of at least one contact that needs to hear about this technology or one application where this can be used in the development of complex structures. MTEC is a small business which specializes in delivering structural analysis and design solutions to complex problems. We can deliver original equipment manufacturer or OEM level design and analysis products because we come with deep OEM level experience. FEM analysis has been at the heart of MTEC's skill set from the start. We have one of the most experienced group of FEM analysts when it comes to aircraft vehicle level system development. While working for OEMs, our engineers have developed the current FEM for the JSF, the C5, and the Gulfstream G500 and 600. While at MTEC, this work has continued with several proprietary projects. MTEC has a close relationship with the NAVSEA structural support community with many completed and ongoing projects with PMA 207 and PMA 290, where MTEC is the only non-OEM to have an approved outer contour modification to the P8A. In addition, our SBIR team includes one of the United States' most experienced retired shipyard submarine architects with over 40 years of experience, which includes setting the Columbia hull and missile tube diameters and lead architect of the Jimmy Carter. Also, we work with design and testing organizations at Southwest Research Institute. These groups have designed, analyzed, and tested structures for the deep diving Alvin and other specialty submersible vehicles. It's a great team with deep experience to understand the Navy's needs. This SBIR topic was written and sponsored by the Navy engineering community to fulfill a need. That need is to enhance the efficiency of bringing the next generation of submarine platforms into service by streamlining the process of approving engineering calculation packages, which are based on FEM analysis. The Navy engineering community is asking for a set of processes and parameters that can be referenced when new structural analyses are performed and evaluated. The key is to have this guidance available when the next submarine development specifications are written. The topic solicitation spells out some of the complex submarine geometry that the guidelines need to cover, which include large hull inserts, tank boundaries, and bulkhead taper regions, among others. This list refers to detailed design around complex structure rather than the overall ring-stiffened hull. The structures around the Virginia payload module hull penetrations are good examples. The guidelines also need to cover a wide range of submarine geometries and operational environments, large or small vehicles, deep diving or typical operational depths, rescue submarines to boomers. Moreover, the guidelines need to be validated through physical pressure tests. Full-scale structural tests of a complete submarine structure are impractical. Therefore, validation of the FEM guidelines to representative structural component tests are critical to building confidence in the analysis solutions. Also, the guidelines need to be applicable to the range of finite element analysis programs and techniques used in the industry, so it's not difficult or costly for the Navy or suppliers to apply them. As I mentioned, the world in many ways is now being designed through FEM analysis. Any aircraft, ship, your cell phone, probably the chair you're sitting in was designed with FIM. The reason is the never-ending push to make things better, stronger, lighter. This push for higher performance is clearly present in submarine design to increase their speed, stealth, and usable internal volume to make a more effective weapon. At this point, the creation, analysis, and documentation of FIM analyses make up a significant portion of a submarine program's non-recurring development budget. Unfortunately, it is not uncommon for the different design and approval organizations to disagree on the adequacy and accuracy of a chosen FIM analysis approach. The only way to prove the accuracy of an approach has been to rework the analyses with much higher level of detail, which is costly and disruptive to schedules. In our estimates, avoiding just a couple of such occurrences could save a program approximately $1 to $2 million per occurrence and avoid schedule slips of 8 to 10 months each time. And that cost estimate does not include the collateral cost of schedule impacts, which can be high. Real cost and schedule data on such occurrences exist, and we can point interested parties to the right program office if they want to know more. Please reach out. But how can these expensive disagreements in FIM approach be avoided? It seems obvious to have a manual or handbook of FIM procedures. Both the design and approval organization could point to the reference to evaluate a given FIM analysis approach. The problem is that this manual doesn't exist. Not yet. MTEC's solution is to fill the need for a validated manual for complex submarine structures and promote agreement between the shipyard and Navy engineering organizations. So what is MTEC's solution to the Navy's challenge, and how is it created? Our solution is an actual guidance manual of FIM analysis of complex submarine structures. This manual will answer key questions such as when one should use solid elements rather than shell elements, or what mesh density is required for the needed accuracy. To create the guidance within this manual, MTEC has created a process that utilizes a design of experiments approach using optimization and statistical routines. These technologies are used to coordinate, automate, and evaluate many thousands of analyses, the results of which are distilled down into easy-to-use FIM analysis recommendations. These recommendations are designed to ensure the level of accuracy required while still providing as much flexibility in their approach as possible. In addition, the validation analyses themselves form a benchmark which analysis communities can measure their existing processes. I mentioned validated analyses. While the topic solicitation calls for validation testing within Phase 3, MTEC wanted to reduce the project risk by performing validation testing within Phase 2. We have developed an innovative and cost-effective testing approach which provides data for the full strain field in the area of interest, which is ideal for comparison to FIM results. This approach has already proven itself in the successful correlation of our initial geometry. The key feature of MTEC's guidance manual is that it fills a need where no solution currently exists. Moreover, our rigorous statistical approach identifies those key geometric and analysis approach parameters that make the biggest impact on results accuracy. The extra benefit is gaining flexibility for the less critical parameters. This flexibility will allow design organizations to continue to use most of their current analysis approaches and be informed when accuracy will be compromised. In addition, the guidance manual's documented validated analysis examples can be used by design organizations to compare and validate their existing methods. Basically, if an organization feels their FIM analysis methods are correct, we'll give them the opportunity and the tool to back that up with data. MTEC's guidance manual will create an improved basis of agreement between the design organizations and the Navy engineering approval personnel that will lead to reduced rework, decrease design costs, and maintain schedules. In the long run, even accelerated schedules. It's critical to look at where we are in the development process and the next steps. Of course, the analysis validation through the scale model testing was one of our key milestones, which occurred in March 2020. This coincided with our initial draft form of the guidance manual. We are in the process of developing our analysis guidance with complex geometry, currently with a validation test scheduled for summer of 2021. We expect the prototype guidance manual to be complete in the March 2022 timeframe. MTEC seeks to validate the analysis guidance through a large-scale test using production-level fabrication techniques and geometry in Phase 3 if awarded per the topic solicitation plan. In addition, MTEC seeks to continue to expand and validate the guidance manual beyond 2022 with the goal of facilitating the delivery of future submarine hull systems to the warfighter rapidly and at a better value. MTEC looks to tailor the guidance manual to meet any specific program needs, support deployment and education in using the manual, and to complete the validation process, which would require some additional testing. To be ready to apply these savings for the next submarine development program, time is of the essence. In 2015, Dr. Tim Arcano, at the time technical director at Carderock, laid out the general timeline for preparation for the next attack submarine and emphasized being ready for the 2024 timeframe. If that estimate is close to accurate, then the manual expansion and validation needs to look for acceleration of the schedule moving forward. In the near term, the manual can be put into a form to be useful for design organizations, but to really make the full impact, the planned family of complex submarine structural guidance needs to be addressed. Also, a validation test plan, including small component tests and a larger scale correlation test, must be completed to assure confidence in the guidance recommendations. The time to start getting this resource into the technology roadmap is now. But the application of MTEC's approach used to create the guidance manual isn't limited to improving the submarine engineering approval process. The approach can inform the FIM idealization of submarine or other naval structures at the preliminary design stage where the biggest impact on performance can be obtained. This could be applied at the shipyards or within the DoD design initiatives such as CREATE and the Rapid Ship Design Environment Program or other design initiatives. The basic results of the guidance manual can also be applied in the shipbuilding and pressure vessel industries, where standards organizations such as the American Bureau of Shipping or ASME with their boiler code could benefit. Possibly the most powerful application of MTEC's technology is through automation of complex structural optimization. Rather than surveying the range of parameters to test accuracy, the approach can be used to find the best parameter combination which minimizes a target value such as stress or weight. For instance, one can vary the number and shape of a hull frames or wing ribs rather than being limited to optimizing their thickness and properties alone. MTEC already has plans to explore this technology for composite geometric optimization for aircraft geometry. Finally, we know from experience that detailed FIM guidance is lacking in aircraft development as well. To summarize, MTEC has developed an answer to the Navy's need that will result in a decrease in the risk of analysis rework and leading to cost reductions and schedule accelerations. In addition, the validated guidance increases the confidence in structural analysis results, increasing the safety and performance of future submarine designs. For the next submarine development program to benefit from the results of this project, time is critical. We look to start the conversation about how we can best understand and meet more specific program requirements in efforts beyond the SBIR Phase 2. We are looking for advocates within the Navy program and engineering support offices to look how we can be ready for the Navy's future needs. Also, we'd like to talk with industry partners such as the prime shipyards to understand their perspectives and where we can work to incorporate their processes within the guidance manual framework. All of this working towards more efficient and effective future programs. Please reach out with questions on how we can continue the conversation and demonstrate the benefits of our guidance as the program continues. We ask that you please pass on any contacts that need to know about this technology and any projects that could benefit from this guidance manual or the potential for structural optimization that the methods support. I want to thank you for your time and look forward to talking with you.